Okay, guys, let's get started. So as I said, I'm gonna publish the grades for the true or false part. As I said, it was out of 42 and the average was 30, so I would say it's a good number. And then next time, or maybe the time after, we're gonna also talk about the actual questions of why, yes or no. Sometimes people are kind of confused, so we're gonna talk about that.
I was just about to do that.
So let's look at presentations. We're gonna do 2.4 first because you guys need to leave. Probably we're not gonna have all the 4 presentations today, but let's see how many we can, and then the rest will be on the. Okay, go ahead.
Okay. Hi, everyone. I'm Alex Chen. I'm a first-year master's student in the ECE department.
Well, this is Yukon. This is Steve.
And today we'll be presenting the paper on the data-oriented programming on the expressiveness of non-controlled data attacks. So I'll just start with the problem statement. And essentially, even with modern control flow protection, which we just had a quiz on, there are still a lot of vulnerabilities via the non-controlled data. So basically just the values themselves rather than the flow. And compared to these control flow attacks, there are limitations on what can be achieved through just touching the values and not really controlling any of the flow. So the question is, with the control flow defenses as a given, how far can an adversary take these non-controlled data exploits? Yeah, so I'll start with the background now. And so I'll just talk a little bit about control flow attacks. So some of the most common control flow attacks are code injection and code reuse, the most typical of which is return-oriented programming. And essentially so these are the most common exploits today. Then I'll talk about how we prevent these control flow attacks. And when I say prevention, is mainly just a high degree of probability that you'll prevent these from happening. So some of these ways of maintaining control flow integrity are address space layout randomization, data execution prevention, and protection of code pointers, as well as timely randomization of code pointers. And so these kind of just randomize the memory layout, as well as preventing executable code from launching from places that you don't want it to, as well as guaranteeing that code pointers are valid, and also re-randomizing the memory layout during the runtime, so the attacker can't take advantage of it, even if they know where the memory is. And now we'll talk about non-controlled data attacks. And so non-controlled data attacks typically have a lot of limited expressiveness. And what that means is that because you only have a couple of vulnerable data bytes, you can't really do as much as you could with typical control flow attacks. And so you have limitations on what you can do. But even with these limitations, a lot of exploits are still possible. And they've shown that this paper has some examples on that you could achieve some information leakage, execution of untrusted code, as well as privilege escalation. So the question is, can we achieve rich expressiveness while maintaining the complete control flow integrity? And then if so, what can we do with it? And so this paper proposes a technique called data-oriented programming, or DOP for short. And they created a way to achieve rich expressiveness by chaining together data vulnerabilities, specifically non-controlled data vulnerabilities. And it's similar to how return-oriented programming uses chained instruction sequences. So essentially, this results in giving the adversary control to perform arbitrary computations within the program's memory space. And in other words, you can basically just force the program to do whatever the adversary wants. And now I'll hand it over to Will to talk a little bit more about the methodology.
Cool, thanks. It's my cat with a very dapper bow tie on. So I'm going to give you like a very high level overview of how this paper works, how data-oriented programming works, and if you have any questions about the details, feel free to ask them during Q&A, because it is a little bit on the complicated side I found. But generally, right, just to summarize kind of what we're saying, we want to do the same thing as return-oriented programming, right? We have a memory vulnerability and we want to attack, the attacker wants to execute some of their own code. But the key trick here is that we want to avoid any potential control flow integrity mechanisms, right? So the programming, you're jumping all throughout the code of the program that you're exploiting. Here, we just want to be able to run in the normal way that the program would execute and completely avoid any defense mechanisms that would, thank you. Yeah, that's a bit better. Avoid any defense mechanisms that would protect against that. So the fundamental idea that the authors present in this paper is they term data-oriented gadgets. These are just really small operations, small snippets of code in the normal execution of the program that can be used to perform various operations on different regions of memory. So, in this particular example that they provide, they start with this buffer overflow in line 7. Once the attacker exploits this buffer overflow, they're able to overwrite the stack and control all of the other local variables in this function. Now that they control all of these local variables, they can start doing things like assignments to memory. So they have a pointer, the C sense, they have a pointer and they want to assign a value to particular address using that pointer, or they want to perform some kind of addition. The authors also identify a few other operations like loading or dereferencing and so on and so forth. And so those individual operations are what the authors call their data-oriented gadgets. So in order to actually execute these gadgets, the authors need something called a gadget dispatcher, which loops over these gadgets and executes them one by one. So taken all together, the attacker can control all these local variables using their buffer overflow, start assigning different values to different areas of memory, start performing basic arithmetic operations, repeatedly loop over these lines of code in the kind of natural control flow of the program, and then use that to perform whatever operations they like on the program that they're exploiting. So yeah, they define like a kind of a minimal language that we call MIDDOC, which summarizes all these different operations that they consider. They demonstrate this language is Turing complete, so it can in effect simulate any computation that you want to do. So I guess just to give like a kind of a high level overview of how the actual exploitation process for data-oriented programming works. First, you identify a memory vulnerability and gadgets around that vulnerability. This is like an example from Wireshark, which is a common analysis program. Once you've identified that memory vulnerability and gadgets around it, you then create the MINDOC program that you want to run. You kind of map that to the gadgets that you found in the program and around the memory vulnerability that you're looking at. And finally, there's this kind of expensive step that the authors term stability verification, where you look at all these gadgets, you look at this program you want to run, you do a sanity check of, hey, can I actually get this program to run? And if you're successful and you can stitch these gadgets together in a way that allows you to run this program, then success. Otherwise, you kind of go back to step 2 and see, all right, well, what other kind of computation can I run with the gadgets that are available to me? Yeah. Cool.
Yeah. Thank you, Will. So let's move to the evaluation part. So in this part, the author tries to organize the evaluation to 2 questions. Question 1 is how often? It's like how prevalent and reachable can we find this data-oriented gadgets and dispatchers in our real-world programs? And the second one is, can we prove the Turing completeness of these gadgets so that we can make more severe attacks? Well, this is the 9 benchmarks that are used in this paper. You guys may be familiar with some of them. They are all very typical programs in the real world. And for the first question, the author tried to prove the prevalence and reachability of gadgets and dispatchers. And he gave us a very clear table of statistics. And we can find that in the 9 benchmarks offered, we can find over 1,000 dispatchers and over 7,000 data-oriented gadgets. And based on this, we can say that dispatchers and gadgets are actually abundant in this real-world programs. And for the second question, can we just prove once we have found these gadgets, can we prove the Turing completeness of them? So the author has offered us many examples and case studies, and I'm gonna just pick one of them, of the Wireshark, to illustrate. Wireshark is a very normally used package analyzer in real world. And this is a piece of the source code from it. And from the first function ahead, we can easily find that there is a fixed size buffer PD, and we can easily think of overflow it. And the overflow can be easily used to override other variables in the function also. And this variables actually pass into the second function. And the second function is the function that really contains the gadgets that we needed. And specifically speaking, we can find many different kinds of gadgets, including different operations in this function. And then these gadgets can be used to form the main dope offered by the author and to prove the Turing completeness of it. And at last, we also can have a dispatcher, which is the third function, which can serve as the loop so that we have an infinite number of gadgets. All of this can help us to make more severe attacks. And that's pretty much in the evaluation part. I'm gonna pass it to Steve.
Okay, cool. So we've already talked about what is COP is. Let's talk about some like defense and conclusions related to it. Okay, so as for so we propose two kind of defense mechanisms related to it. One is the memory safety and one is the data flow integrity. So what is the memory safety then? So as we know, like in the DOPs and for those gadgets and for those like data variables of those particular gadget operations, right? They're on the stacks. We're not saying like their arrangement on the stack will change. We're just simply talking about their pointing positions or their like the reference of what they are referencing to is going to be changing. So in other words, if their variables is going to have like a memory, like for example, referencing exceeds the desired memory referencing, we are probably stop the program or something like that. But well, it will cause additional overhead because you have to check each of the operations, right, intuitively speaking. Okay, as for the second one, data flow integrities. Well, this one is a bit of related to another paper which is called Android. Well, this is not related to the current papers, but I just want it's interesting to bring up this topic to talk about it. I'm not saying you have to use the Android ideas to implement this defense mechanism, but you can just use these big pictures to try to defend. So what this idea is, you are pretty much going to set up like a canary or something related to that, but like the size should be equivalent or maybe less equivalent to the original data. But by doing that, it will cause overhead, right? Because it will have almost as if if you want, let's say 10 data variables, you need like 20 amount of storage space for that because you have to store additional like data like storage for your like checking variables. Okay, we also talk about like some other preventions related to that, which is the fine-grained data plan randomizations. So on the left side was the desired result we want, right? So the store address of the previous is equivalent of saying the load address of the next gadgets, right? So they're basically referencing to the same memory space. But what if we try to randomize or shuffling around this, memorized space, which we got on the right side of the pictures? They are not like referencing to each other, which means the gadget chain will be broken in this case. And for the hardware and software false solution, I won't talk a lot about it, but you just need to know that there exists such thing because they kind of saying that it's partially true, but it's not like necessary to compare to like other defense mechanisms. Cool. Okay, so we've already talked a lot about the DOPs. Just have a quick wrap up. Okay, so what is DOP? It's just like it's different from the RLPs. Well, one key difference is just it cannot be detected by the CFA, which is the control flow integrities, right? And it kind of highlight the need for us to raise the security concerns related to these areas. Okay, so some of the future works I proposed was that the proposal said the TOP was basically mainly on the those small gadget chains. So what if we try to develop a model or machine learning models or any machine learning models that could run through those gadgets and trying to see if there's like
if try runs through the program and try to see if the programs contain those malicious gadgets which we mentioned, and then we'll probably stop the program, or we can just replacing some parts of the program, something like that. Okay. And the second part was that well, it's kind of related to embedded systems, right? So as we know, like embedded systems are kind of like more vulnerable compared to other PCs or things like that. So its security awareness hasn't been like that much like mature compared to the PCs. Well, if like we have a DOP attack on the embedded system, it will completely broke the embedded system, right? Because in this case, I would say it's kind of like an overkill. Because the primary purpose, like if you try to like develop a defense mechanism for that, it will be not worth to do it, because like the purpose of that, the purpose of the embedded system was to like small, and you don't want to just have like too much like not core related functions in it, right? Which will kind of lower down its performance, and no one would buy it. So okay, cool. I think that's pretty much all for the DOPs. And now let's move on to the Q&A sessions. So if you have any questions related to the DOPs.
Thank you, guys. Questions?
Yeah, great job with the presentation. I really like this paper too. Something I was curious about is it mostly depends on like long jump and stuff that's specific to x86, and that was kind of the main focus of the paper. Do you know if they've done any work since then on like RISC architectures like ARM or MIPS? I know they mentioned in the paper, oh, like it'd be harder to do. That's a future work. You know if there hasn't any future work since?
No, because the evaluation part is actually limited to the x86, and they also haven't provided any other platforms, I think. Yeah, I don't know either.
So I think it will probably like provide more details about RISC-V, since this paper was from like 2016, right? So it's pretty much like it's like slightly old paper. So there will definitely be some like new papers or new like researches related to RISC-V.
Yeah. Any other questions? Yeah, this is just a very different kind of way of attacking systems, right? So it's not like overflowing your buffer to kind of run any instruction. No instruction is actually being executed, only the data is being modified, right? So all the good things you can do with control flow integrity and all those things won't work on this, because this is essentially not running any program on your computer, right? It's just manipulating data. And so we need to kind of look, even a step beyond what we have right now. All right, thank you guys.
Thank you.
Okay, just one quick comment. Try to stay in your time limit, okay? Don't go over. I know there are lots of exciting things to say, but G11, 2-1. You're in 2-2, right? Okay, so first it's gonna be 2-1. You're 2-2, right?
Yeah.
So this group, yeah, these groups kind of came out of order. They were 2-4, now 2-1, and then you guys. Right, sorry. Are we? No, just connect to this. Oh. Oops.
No. 810-188-2955. Make sure your audio. Actually, maybe not. Zero recording. Yeah,
Yeah, just be like yourself. Okay.
Yeah, join it. You can join audio and then mute. And mute your laptop. There.
All right.
All right. Hello, everyone. My name is Jacob Hoyson.
I'm Aganorian.
I'm gonna have that.
And we're presenting a paper that has to do with a physical model aware rootkit that attacks PLCs.
So to kick the presentation off, the problem that the paper is really tackling is this idea of infecting a PLC, which is an industrial control system, that takes in data from, say, a generator or something. It's input into this PLC, and it outputs this data to a human control interface that is closely monitored, right? But like every good story has an antagonist. So introducing Harvey, which is the name of the malware. It's also the name of a Batman villain. I don't know if anyone else is familiar. But what it does is it actually infects the physical sensors, takes in the input from the PLC, reinterprets that data, and then pushes out infected PLC IO, which is then monitored by the operators, but it's completely like unassuming because it looks exactly the same. It's like kind of reminiscent of like a replay attack. You're just kind of showing the data as it was before while the system's going into meltdown, really. So first we kind of have to introduce like kind of what a PLC is, right? So the PLC is an industrial grade computer that's used in several aspects of like water treatment, power generation, even in nuclear facilities. And it's designed to operate in harsh environments. And it's pretty much just a computer that's able to process all of this data, like I said, from these input devices, and then simply outputs them to the human control interfaces or via a series of LEDs to the operator. So why are PLCs so important? As I said, they control very important processes in critical infrastructure. So while we don't always think about it, these computers control our everyday lives, right? We have power grids that are powered by these things, right? We have water treatment facilities, sewage facilities, nuclear reactors, right? And that poses a threat. If you don't monitor the vitals properly, bad things can happen. Harvey can attack these systems like pretty safely, whether it be through a remote execution or a firmware update. And that's really where Harvey lies, at the firmware layer, right? Through either a local or remote firmware update. So I'll pass this on to Puya to talk about the industrial system model.
So our system model is pretty simple. And the only thing we really are interested in is the PLCs, right? And so we can imagine on one side of the PLC, they're connected to, a series of sensors and actuators that are attached to our device in question. And then on the other side of the PLC, it's connected to this central control unit, which is, feeds these, manages these HMIs that the operators can interface with our system, right? So basically, like the PLC is doing two primary tasks, right? It's reading sensor data and controlling the actuators, as well as like feeding back to the operator. So the purpose of Harvey is to kind of be like this two-way like data manipulation attack. So what it's going to do is it's going to read sensor information. It's going to parse that information using some kind of internal model of the system. It's going to feed back fake data that appears to be legitimate. And at the same time, it's going to be able to parse commands from the operator. And instead of like, so if the operator says set the frequency to 62 hertz from 60, maybe Harvey does the opposite, but it's going to relay that information that the operator wants to see back to them. And so like, how do they go about actually doing this? So the reverse engineering method was like, it's pretty in depth, but the key thing here is that like, we want to identify the specific instructions that's writing to our GPIO registers. And so, through the series of, they use a JTAG, they get the device firmware, they find where the code starts, and they can essentially like find all the like important instructions. The most important one being like, a timer interrupt that calls a function that modifies GPIO. And from there, they can essentially just replace the function, call some malicious code that they add because there's a lot of unused memory, do whatever they want right back to that register and then jump back to the program execution. It's like nothing ever happened. And so like the uniqueness with this paper is their physics-based approach. So, in one case, if we infiltrate a system, we can just inject, like malicious commands willy-nilly, just break the system, but that's not really stealthy and we'll get caught right away. The next method is like a record and replay attack, which has actually been employed in the field, which we'll talk about a little bit later. But the idea there is that we just listen to the data for like a few hours or a few days, and then we kind of just like replay that recording. And this works for like really stable systems like a nuclear centrifuge, where like these centrifuges are just rotating at a fixed frequency for long periods of time, right? But power systems are a little more dynamic. There's a lot more like random variations and like cyclical pattern that we can't really like predict. So we kind of have to like understand the model of the system. So if we input some, if we change some input parameters, how does the output actually change?
Okay, now let's talk a bit, talk more about the attack. As we mentioned, the attack has a physical awareness. The physical awareness includes three parts: control, monitoring, and the distributed control and monitoring. Regarding the control, I can say that each dynamic system can be defined by the first and second mathematical equations. The ABC, the matrix that define the dynamic of the systems. X is a vector that defines the state of the system. U is a control command that we want to talk about it. And omega and epsilon is the noise. Okay. Regarding the control, in normal case, the U will be generated or calculated properly, but in the attack mode, attackers try to produce the fake control command or U vector in order to increase the damage to the systems. Okay. Regarding the monitoring, another option of the attack is to remain still. Okay. So in this case, the attackers try to record the history or the data for you about, for example, many days ago before the attack starts. When attack starts, try to using this history for you that the operators who, for example, with monitoring the system cannot figure out that the attack starts. And regarding the distributed control and monitoring, I can say that in the physical world, in the physical power grid, the physical power grid can be separated into different zones, and each zone can be controlled by one, two, or more than PLCs. The attackers in this case, since it has the physical awareness, is only in order to damage the system, is enough to, for example, attack one or two PLCs. But now let's talk about in the real world. In the real world, the power system, the power that requires to produce or inject into the system can be determined by an algorithm. It's called optimal power flow. Okay. In this case, or in this algorithm, try to minimize the function. Okay. Try to minimize the cost function. C of x y, which is the function of x and u. X is a vector system and u is a control command. Okay. While these three constraints should be satisfied. Okay. When you are in the attack model, attack scenario, the attackers try to produce the fake u that maximize the cost functions instead of minimizing the cost functions. Now let's talk about the different model of the attacks. Okay, this is the real test bed that the authors mentioned. We have a different scenario for attack. The first one is a steady state system. It means that the attackers try to repeatedly using the heavy load circuit breaker, open or close triggering, while the system keeps its power stability. Okay, and the second scenario is adversary optimal control attack. And now let's talk about this kind of attacks a bit more. In the first one, as I mentioned, the systems keep its power stability. Okay, so approximately the power is still the same, but as I mentioned, the power of the attack model is remain covered and still. So the operators who monitor the system cannot detect that the attack is starts. Then another scenario for attack is adversary optimal control attack. It means that it tries to produce a control command, fake control commands, okay? That instead of minimize the cost function, try to maximize the cost function, but by considering some, for example, assumptions. The first one is remove the triggers or threshold that make sure the system works in the safe zone, okay? And also, in this case, the operators cannot detect the attack starts because in this case, instead of using the optimal power flow algorithm, try to minimize the cost function, the attackers try to use the malicious optimal power flow. And again, the uniqueness of the attack is to remain covered and steals from the operator. And you can see if you are, for example, operator, you cannot figure out that you're under attack. And in the history, we have two kinds of attacks to some countries like Iran and Ukraine. Yes.
And then really quickly to wrap up, we have some mitigation strategies. 1 and 2, they're not as interesting as number 3, but real quickly, remote attestation is just having a trusted third party like approve of the firmware remotely. And then the secure boot with TPM we spoke with during class. But number 3 I found was the most interesting. And in this diagram, you can kind of see like maybe it's like trivial to think about, right? That you have like a secondary sensor that's able to be checked against what the PLC is outputting, and then the operator's pretty clearly going to see that something's going on. And there's a pretty quick section of that paper. They had these 3 quick solutions, and this was the most interesting. So this is the one I decided to model. But yeah, thank you so much. Any questions?
Does this like equally affect the different models of PLCs? So like, like Alan Bradley, like Siemens and stuff.
No, so basically this kind of attack, you have to like know exactly which PLC you're targeting.
Okay.
So, every PLC's got different like pin layouts. So, I mean, maybe any other PLC that's like using the same compartment controller in there, the same like layout, that could work.
I think they targeted Alan Bradley actually.
Yeah, exactly.
Yeah, Alan Better.
So that's like the most common one. And these guys actually put it on that.
Yeah, and then also, the paper did say that it could be generalized given enough time, because they did put a lot of work into breaking that PLC. Yeah, Matt.
Yeah, great job.
Thank you.
Something I don't know much about what PLCs really are, so I'm curious, like, is there something unique about them that makes it hard to fix this problem? Like, you can't take a generator offline for the LA grid, for example. Like, is there a reason why you can't intrinsically fix the thing? It seems like something in the middle or alternate sensor was the better approach.
That's what I personally thought, although I did find it interesting that they mentioned the secure TPM approach, because that was also a question that I had and I could not find a solution for in the paper. I don't even know why they mentioned the secure TPM when honestly it probably could be built into the PLC itself, but maybe the Alan Bradley
Yeah,
simply
the
didn't have.
problem is legacy systems for PLCs.
Yeah.
Because these are essentially PLCs so scattered in like oil pipelines and electric pipelines. And you cannot take them up. If you we actually have some ideas for securing this. If you talk to people in oil or critical infrastructures, they just don't answer you. They're not gonna, shut down their systems because first of all, they have no idea how their system works. It's been something that like 50 years ago, somebody works on it and it just works. So they cannot, make it offline. So these is like very complex systems that you cannot really take it off. So if you want to do anything, it has to be some form of external kind of bump in the wire or anything like that to kind of fix.
So we're not like making new PLCs.
If you're making a new PLCs, then do all these other things.
But I guess it sounds like that's not very common. Like the problem.
It is, but I mean, it's just like 90% is legacy and then 10% is that. Maybe next week we can set up and then we can continue talking about this. Yeah, you guys can. Is it okay if you do it next time on Wednesday? Are you around for next time? Is it okay?
The answer should be yes.
All right, sorry about that, guys. On Wednesday. Yeah, yeah, sorry. I mean, these guys would be. All right, yeah. So before we let go, yeah, this is one of the interesting examples of when you're actually using physics to get your malware, right? So the malware, we talked about different viruses and stuff like that, but when you actually like target it specifically for a physics problem, you can actually do much more powerful attacks. So that's kind of one example. No, I mean your examples. Sorry for the 2 groups that didn't present. We're gonna do it on Wednesday, first thing in the class, okay? Group 3 and group 2, yeah. No, there is no sign. Oh, really?